All right, so just a few preambulatory, whatever, some beginning comments. First, I want to thank Jacob for the opportunity. These workshops have been a great encouragement in the last months, and it's been wonderful to hear a variety of talks and to see people from all over the world. And be reminded that we have pretty cool jobs to study what we study. So thank you, Jacob. The second thing is I'm going to do something today that I've never done before in giving a talk, which is potentially read bits from my own writing. And I don't do this, but I've had a particularly difficult few days, but I really wanted to be here and share this information about Grete Hermann with you. So please do, I beg your indulgence if I read a little bit to maintain coherence. All right, so let's begin with just a little bit of biography, because who was this person? Her name was, of course, already mentioned in Adam's talk, and I thank you for that shout out. But I think in some of this biographical background, and as you get to hear a little bit about who she was interacting with, it will become an even deeper mystery why, for instance, her understanding of entanglement as a new property that comes about in quantum mechanics, although she doesn't call it entanglement, her realization that there are different, one might construct a theory of hidden variables that involves context dependence versus context independence, and various other insights she had before the usual historical first mentions of these things. Why, nevertheless, her ideas are not brought into the mainstream. Yeah, that mystery will just be deepened, I think. So yes, Grete Hermann, born in 1901 in a small town in northern Germany, Bremen. She matriculated at the University of Göttingen in the early 20s, and if you know anything about Göttingen in the 20s and 30s, it was in its halcyon days with respect to philosophy and mathematics, and both theoretic and experimental physics. So for instance, she overlapped while she was there with, well, she was a student of Emmy Noether, the first and only female doctoral student of Emmy Noether. Bohr was there in mathematics. It was Hilbert. Paul Bernays was there and was a student who, along with Reichenbach, became teacher of Karl Hempel. Von Neumann was there. Felix Klein was there. Richard Courant, now of NYU mathematics fame. There was also Bohr and his students, Oppenheimer, and future Nobel laureate Maria Goeppert-Mayer was studying there in those years. And of course, also in physics were Heisenberg, Jordan, Hund, and experimentalists like James Franck, who had weekly conversations with Bohr and his theoretic circle. So there was just a lot of crossover between the philosophical, the physics, and the mathematical circles in these days, and a really rich atmosphere to study. So she completes her PhD under Noether, and she writes this dissertation on the question of finitely many steps in a theory of ideal polynomials. And this dissertation is, I guess, still cited in certain computer science literature. But what's interesting is during those years, she sat in on some of the lectures by this Friesian neo-Kantian scholar, Leonard Nelson, and she became very intrigued with Nelson's natural philosophical project, and in fact became his literary executor along with Minna Specht, and was one of probably his star pupil, I think it's fair to say. And there's a quote from Noether that, you know, she studies for 4 years mathematics, and then she discovers her philosophical heart. So she sort of moves from philosophy to physics, from mathematics to philosophy and physics, and becomes very active, not only in the political aspects of Nelson's philosophical school, which was the Neo-Friesian Schule, the Neo-Friesian school, which attempted to bring back this rather somewhat obscure neo-Kantian interpretation of Jakob Fries. And I will mention a few key tenets of Friesian neo-Kantianism to help us understand what Hermann is doing in her interpretation of quantum mechanics. But what is important to know right off the bat is what is important among many other interesting tenets is that engaging in critical philosophy with Nelson and in the Friesian context meant not only a theoretical sort of deep cleansing, but there were also practical aspects that were expected to be implemented that came out of these claims. And so the project of theoretically deducing these practical aspects of Kantian claims was done through application of Kant's transcendental schema in the Friesian manner, which, among other things, argued that Kant's 12 categories of the pure concepts of understanding, if you remember these 12 categories, a subset of those 3 relational, one of those is causal relations, right? So these are the conditions that make knowledge possible, and of course, natural knowledge possible, ergo scientific knowledge. And so one of the things Fries did was that contra Kant, the a priori concepts of these categories do not need to be adhered to strictly, but more in an analogous sense. They are to be interpreted instead as empirical concepts, which form sort of a loose pattern, and that's where the analogy aspect comes in. So they provide a loose pattern for organizing sensory experience, not strictly deductive categories, a priori categories. So in this way, Fries was attempting to reframe the Kantian critical philosophy as an explicitly scientific method for obtaining, ordering, clarifying, and ultimately unifying all knowledge. And it's this aspect of unifying all knowledge that Nelson picks up on, and in fact, Nelson considered his project of axiomatizing all natural knowledge to be very much in sympathy with Hilbert's axiomatic program. And so Hilbert and Nelson were very close friends and colleagues, and discussed quite a bit together this project of unification. Now, because Fries had relocated these Kantian categories of the understanding from the domain of the a priori to that of the empirical, it makes sense then in the latter half of the 19th century that other neo-Kantians frequently accused Fries of psychologism. That is, they said, you're rendering Kant's schema in a way that makes it overly dependent on the intricacies of human cognition. And Nelson presumably wanted to avoid those accusations, and he did so by trying to recover, using a Friesian framework, but trying to use the framework under strict methodological guidelines, right? So working backwards from the data of experience to an analytical principle, and then trimming away all the excess fat, that propositions that actually played no role in that walking back from the data of experience to that analytical principle. And in this way, this sort of regressive analytic form, you can get rid of all that's unnecessary, including vague or confused judgments, and instead transform your propositions into very clear, coherent, and ultimately unified within this universal framework concepts. The practical task that came out of this theoretical sort of regression to first principles involved giving scientific grounding for not just scientific claims, obviously, but educational, legal, ethical, pedagogical systems. And so in that way, it really is an attempt to recategorize and re-understand all of human knowledge. So I note here just one point of departure for Nelson from Fries, because it will become important in my analysis of Hermann, namely that despite Fries's reinterpretation of the categories as analogies, Nelson maintained the hope of constructing new systems of knowledge by applying at least the category of causality in a strict and absolute way. So for example, Nelson used his natural philosophical method to deduce a rigorous causal procedure one should employ when making moral decisions. I quote, or I will give in the end of the reference as a discussion by Fernando Leal in a nice paper where he describes in more detail this interesting application of causality to a procedure for making moral judgments. So it was back to Hermann, so it was in her close work alongside Nelson, but her enduring interest in physics and mathematics, that she was inspired to address the perceived conflict arising between the Nelsonian or any neo-Kantian worldview and the worldview of modern physics. And of course, we all know that other neo-Kantians had been hard at work defending Kant's claims with respect to special relativity and general relativity. And there's a bit of work that's been done on quantum mechanics, although the way that the better known neo-Kantians dealt with causality in quantum mechanics is rather different than the way Hermann does it. And I'm working on a paper right now that spells out in more detail exactly how she departs very richly and interestingly from the causal stories, the stories about causal and the causal principle that other neo-Kantians like Carnap, Cassirer, Reichenbach, Kojev are providing at this time. Okay. Of course, I mentioned the theoretical applications leading to pragmatic applications, and it wasn't just that Nelson wanted to render all of human knowledge according to the 12 categories in a unified framework, but also there's political activism and other lifestyle things like secular worldview, so leaving the church, vegetarianism. There was no explicit command to remain single, but there was an idea that having children or having a family would detract from your ability to contribute to the group's political workings. So she's actively working in these years with various political associations, like the Internationale Soziales Kampfbund, which is the ISK in Berlin, that was publishing against the Nazi regime. And so she was an active critic of the Nazi regime and of their political views. In the midst of all this, she writes an essay in 1933, which Guido found the manuscript for in the Dirac archives, where she's trying to defend determinism in quantum mechanics. And it's a fantastic manuscript, and we have analyzed it in some detail in an article in 2017, which I'll reference at the end. And there's just a few quick points I will make about her 1933 essay, but she changes her philosophical perspective rather drastically between 1933 and 1935. In those years, she goes to Leipzig because of the promise she shows in that manuscript, and that she sent this manuscript to the physicists at Copenhagen. So Dirac read it, Heisenberg read it, Weizsäcker read it, Bohr read it, and they read it with such interest that they spent a long time talking about it together, and were planning a response to her defense of the possibility that quantum mechanics is still deterministic. So they took her writing seriously, and interesting enough that they were writing a response. And in the end, she did not go to Copenhagen right away. She would in later years, but instead went to Leipzig to work with Heisenberg. And so it's during her time in Leipzig that she writes her 1935 essay, which I will consider the locus classicus for her mature interpretation of quantum mechanics. And she publishes a few other things, like a short version of this essay is published in Die Naturwissenschaften, which is one of the most important physics journals of early 20th century Germany. And most of the extant work on Hermann primarily concerns this 1935 essay, but more interesting work is continuing to be done on here. So here are some pictures of Heisenberg, and at the top with a lovely short tie, guys. Let's see if we can bring those back in fashion. And von Weizsäcker at the bottom, who was deeply influenced by the conversations he would have with Heisenberg while in Leipzig, and they maintained correspondence throughout her life. Some other fun pictures of Heisenberg's Leipzig Kreis in the early 30s and mid 30s. A lot of ping pong was played, a lot of Kant was discussed. And I just include these pictures because it's nice to remember times when people could sit together in the same room and discuss things. We will have those days again, I pray. In the 30s, she goes into exile, and she's in France for a time, and Denmark and England. She has a marriage of convenience to Edward Henry, and so sometimes her publications are Grete Hermann. The Nelsonians in England found the Society for the Furtherance of Critical Philosophy, which has to do with taking some of the Nelsonian pedagogical aims and Socratic method in teaching and making them more widely known. She continues to write essays on physics and on philosophy of physics in these years. After the war, she comes back to Germany, and she's mainly the director and a professor of philosophy and physics at the Pädagogische Hochschule in Bremen. So she doesn't have as much time to work directly on the old problems in quantum mechanics, but she's continually writing about these and maintains an active interest in the physics. But before she can go and actually take leave of her job and work with Weizsäcker, who was then head of one of the Max Planck Institutes, before she can go and work with him again on these old questions from the 1930s, from the good days in Leipzig, she is unable to do that and eventually passes away. Okay, so for historical reasons, I want to point out very quickly some of the key tenet aspects of the 1933 manuscript, which was never published, but again sent to Copenhagen, and so read by Bohr and his circle, and also by Dirac. Dirac's calculus, Dirac's version of quantum mechanics, had been published just earlier in the 1930s and was famously obscure, obtuse mathematically. Hermann was not daunted, and her entire essay is based on the Dirac formalism. But the purpose of this essay is to use Dirac's operator calculus to investigate on solely physical or formal grounds whether indeterministic aspects of quantum mechanics can be sort of lifted out without compromising the explanatory power or the logical coherence of that theory. And she concludes in this manuscript that that you can do this, that you can get rid of those moments of indeterminism without impacting the logical coherence or explanatory power of quantum mechanics in Dirac's formalism. And I don't want to go into all the details that I have on this slide, but one of the things she does is investigate von Neumann's hidden variables proof, no-go proof, and show that it fails. And so the way of hidden variables remains open. Before that, earlier on, she's discussing the strategy of hidden variables, and she seems to notice in the discussion of what these not yet discovered but potentially causally completing variables might be capable of doing. And she says, and here I'm reading the quote from her manuscript, "The possibility remains, however, of discovering other as yet unknown physical quantities, such that the knowledge of their values, together with the position and momentum of the electron, are sufficient to predict the result of the position measurement. These quantities need not necessarily be determinants just of the observed electron itself. They could also pertain to the measurement apparatus used for the position measurement, since this indeed exerts a demonstrable influence on the electron." This quote from her manuscript, along with quotes later on where she's concluding that quantum systems and measurement systems need to be treated as wholes quantum mechanically, have led Guido and I to conclude that she seems to be understanding a distinction between different types of hidden variables, ones that are contextually dependent and those that have no such constraints. So here it is already in 1933, and she would make the same argument in her published 1935 paper. She also has a section in the manuscript just called Neumann's Proof on Indeterminism, where she shows that there is a circularity in von Neumann's proof. And because this has been part of the discussion with Adam's talk and will be more of the discussion with Chris's talk later on, I will exceedingly briefly introduce her strategy here, which is as follows. Von Neumann's proof is a no-go argument and is corollary to a larger theorem characterizing the sorts of ensembles that are possible for quantum mechanical systems. And von Neumann argues that given certain assumptions, including linearity of observables assumption, he proves that it's not, there cannot be dispersion-free ensembles. But it is exactly that assumption that the linear of observables excludes, that Hermann argues excludes already the type of dispersion-free ensembles that he later on says do not exist. So hence the circularity. Right. Fuller details analyzing not just the 1933 version of the proof, which is very much like Hermann's 1935 version, maybe a little bit clearer, in fact, are in the paper I wrote with Guido in 2017, but also in Michael Sievink's Challenging the Gospel, Grete Hermann on von Neumann's no hidden variables proof. And there he gives a nice comparison of he didn't know of her 1933 essay at the time, but of her 1935 essays and proof about the circularity in von Neumann's proof, many proofs, lots of proofs, much proofs, and compares them also to Bell's work in the 60s. So, and whether or not what she's doing is comparable to Bell and sufficient to prove circularity and so on. So I recommend that further reading. I think Dennis Deeks has also perhaps written about this question. Okay, so yeah, I'm not going to talk about the 1933 essay more than that because, again, I take the locus classicus of her interpretation to be the 1935 essay, which she did publish twice, and which was, she may or may not have sent copies of it to many different people, including Schrödinger and Einstein and Jordan, and in which she changes her tune about whether or not hidden variables are still possible. But I did want to point out that it looks like there's good evidence already in 1933 that she's noticed a difference between what we now call contextual and non-contextual hidden variables theories, and that she already has in this 1933 manuscript the proof against a proof for the circularity of von Neumann's no-go theorem based on the linearity assumption. Okay. So now let's now go to the 1935 essay. This is the essay she wrote after she had gone and attended the Leipzig seminars given by Heisenberg and spent many hours in deep discussion with von Weizsäcker and Heisenberg. Grete Hermann has just published a volume of all of her stuff in German, including her correspondence, and it's just fabulous. I finished reading it this summer and I'm working on a couple translations of the major stuff. I think Guido might be too. We'll have to talk about that later so we don't overdo it. But she writes a lot of great letters to her mom talking about how Heisenberg makes her want to climb the walls and things like this. But they nevertheless are having very meaningful conversation. So she writes this essay at the end. She publishes a more general philosophy of physics paper that treats not just quantum mechanics, but also special and general relativity and electromagnetism from a Nelsonian neo-Kantian perspective. And she actually wins a prize for that essay, and it's not published until 1937, but she wrote it at about the same time she was writing this 1935 essay, the title of which in English is The Natural Philosophical Foundations of Quantum Mechanics. And here natural philosophical is an adjective describing the Nelson approach, the Nelsonian, Neo-Friesian, Neo-Kantian, all these adjectives. It's like a hipster ice cream shop way of doing philosophy, right? So the first thing she begins with is a discussion of how she will proceed, and she notes it's important for the Friesian to begin from the data of experience and work backwards. And if the data suggest that there must be revisions to our philosophical viewpoints, then we must make those revisions. It is not vice versa. It is not that our a priori, that there is a priori concepts about the world are sacrosanct. In fact, they can be altered in order to make room for new findings in physics. So she writes very early in the 1935 essay why we need to interpret quantum mechanics. She says, beware, by the way, beware of the portrayals that physicists give to quantum mechanics. And she goes on, and I'm quoting here, for these portrayals by the physicists, understandably, far exceed what has directly proved itself reliable through successful predictions or the correct rendering of observed data. This direct empirical corroboration pertains, strictly speaking, only to the formalism of the theory and its correspondence to the data of observation. So here you see her trying to make and establish a very clean link between the data of observation and the formalism. The conceptual interpretation of the formalism that must necessarily accompany it in every physical theory only receive direct physical corroboration in as far as the corresponding formalism proves to be an appropriate means for describing observed events. Where this interpretation is ambiguous, then one can only make a physical, empirical decision between the different views if they give rise to the different extensions of the formalism. And so I think this is a little bit of her attempting to quash some of the wild claims about causality and other genuine moments of indeterminism that supposedly arose in quantum mechanics by saying that we need to do careful work to reestablish this link between the data of experience and our formalism. And as we shall see, that link becomes particularly hard in quantum mechanics because the things in the symbols we use in our formalism are no longer directly intuitive in the way they were in classical mechanics. And so the bridging of these relata is a more complex process. But we'll get into Kant in a minute. So there are two aspects that I want to discuss from her of her interpretation that are the main bits of her 1935 essay. And the first is this very fascinating retrodictive causality thesis. Guido and I are finishing our book now. We're very near finishing copyright stuff on the debate on incompleteness in 1935. And so in the early 30s, the question of causal completeness and whether quantum mechanics is completable is very much at the forefront of interpretation debates. Hermann herself is giving a very radical sort of solution. She's going to say in her 1935 essay that hidden variables theories of the sort she considered early on in 1933 are not possible, not because of a proof like von Neumann's or anything of that sort, but because quantum mechanics is already causally complete. It's just that we cannot have access to this continuous causal chain underlying all phenomena until after a measurement has happened. So it's only retrodictive causality that's recovered. Nevertheless, the theory is already causally complete, hence incompletable. So I'm going to skip this for now because I think it's less crucial, but before she sets up the retrodictive causality thesis, she spends some time discussing how to properly interpret the Heisenberg uncertainty relations, because unsurprising, the uncertainty relations are the locus of much of the philosophical discussion about indeterminacy and incompletability. She gives a very interesting argument in her 1948 essay later on that is a little bit clearer about why she thinks, quote, subjective interpretation of the uncertainty relations fails. And I'll give you the upshot. It's because she says that the subjective interpretation fails already with dualism experiments. And she says if we restrict ourselves to a subjective interpretation where the uncertainty relations mean just that the position and momentum values objectively pertain to the electron, but the physicist cannot know with arbitrary exactness those things. this interpretation fails already, because then we could not give descriptions for interference phenomena. We could not explain interference phenomena. So again, she's taking her cue for the interpretation of the Heisenberg uncertainty principles from the duality experiments. And of course, this is how Heisenberg himself describes the uncertainty relations in, for instance, his Chicago lectures in the 1930s. He starts with all these conflicting experimental data, and then says the only way to bring these data together into a coherent formalism is by the uncertainty relation. But interestingly, and I want to read this because it's one way in which we can be very clear that what Hermann is doing is not talking about collapse at any point. And she carries on a discussion about collapse of the wave function as being sort of objectionable to her on many grounds in various places in her correspondence. But here in her 1948, she's going to explain why a quote, objective interpretation of the uncertainty relations is impossible. Let's just have a look at this. This is my translation. It's a little clunky. I apologize for that. So we get into difficulty immediately if we ask what happens when, say, we perform an exact measurement of position on an electron with quantity delta Q. Such a measurement is possible, blah, blah, blah. Its results can only be obtained as one of the results predicted by the rules of probability. It leads to a new determinate state of the electron solely in terms of position, fixed within a small uncertainty limit, delta Q, whereas the momentum, which was previously sharply determined, exhibits a large uncertainty interval. If we stick to the objective interpretation of the indeterminacy relation, we get a picture wherein a widely spread wave peak has experienced an influence at the instant of measurement and suddenly has contracted into a narrow, but for that reason tall, and so rapidly divergent wave peak. Correspondingly, an exact measurement of velocity must be associated with a sudden flattening of an initially steep and narrow wave peak. Because of the uncertainty of their results, these processes must pertain to the allegedly, quote, causal occurrences. Now, admittedly, quantum mechanics has established that any measurement of the atomic is associated, or verbunden, bound up with, an interaction between measuring instrument and measured physical object through which the state of the object is changed. But these changes are presented to us here something like wave peaks undergoing very strange processes of contraction and propagation. For example, the idea, inadmissible in modern physics, of a wave train of astronomical proportions that, when need be, can contract from any spatial dimension to the size of an atom in an instant, and insofar as it does this, with an excessive velocity. Even aside from peculiarities of this type, it can be shown that the quantum mechanical formalism has no place for the postulation of such events. So she's clearly has issues with sort of a collapse interpretation of the wave packet. But she's going to say that there's no need for postulating such events anyway, and that is because of the causal completeness of quantum mechanics. So there are two aspects of the causal completeness thesis. She's first clear to say that all the Kantian need assume, and in fact all she should expect even in classical theories, is that for any event there exists some cause which has determined it. She makes this is where she proceeds with a very Nelsonian analysis, saying the concept of causality does not, although we've usefully associated with the idea of prediction, the idea of being able to predict something on the basis of a causal chain is not itself inherent to the concept of causality itself from an analytic perspective. So one can, on this analysis of causality, separate the idea of causality as a continuous chain of cause and events where each event arises because of some cause, divorce that from the conception of prediction with which it's become mistakenly conflated. And so when you divorce the two, then although quantum mechanics presents insurmountable limits on predictability, she has just argued via the uncertainty principle, it still involves these continuous chains. Yes, we may not be able to predict beforehand what the determinate outcomes of measurements will be, but nevertheless, that doesn't mean that the causal chains do not exist and are not continuous, for we may identify them after a measurement. So So attempts to find causal completions via hidden variables theory, for instance, are just futile because quantum mechanics is already causally complete. Now, of course, we're left with the question, why is it that if there are these continuous causal chains, we cannot carry out these predictions beforehand? And it's in describing, answering this question that she enters into discussion of her other thesis, which is the relative context of observation. And here she does some very excellent Bohr hermeneutics. And I believe Guido has some papers under preparation that describe in detail just what a lovely account of Bohr's interpretation of quantum mechanics one can derive from Hermann's assessment. And the reason for this is, I mean, she's not only trained in the mathematics and has had many discussions with the physics, but she's a brilliant neo-Kantian. She's a brilliant Kantian thinker. And so she picks up on these many Kantian influence in both Bohr and Heisenberg that Catherine Chevalier and I think some other people have argued. I'm blanking on names now, forgive me. But she brings them to the fore and explains them very clearly. And one of these is how Bohr's doctrine of complementarity invokes Kantian moments. So yes, in the literature, there are many interpretations of what Bohr meant by complementarity. But what Hermann does in her 1935 essay is very clear. It's philosophically rigorous. It captures maybe the Kantian aspects latent in Bohr, and I will explain that here. So, and it will eventually get us back to the solution of why is it that even though we have complete causal chains underlying physical events, we nevertheless cannot know beforehand. The answer is, and the title of her section is the answer, or the solution, the relative context of observation. Okay, so that is the answer. Let's see how it works. So she first says that there are three sort of non-separable, if you will, aspects of complementarity that we can parse out. One is there's the sense of complementarity between waves and particle pictures that we use at the level of describing empirical data. Then secondly, there's the using the uncertainty principle within a single instance of either the wave picture or the particle picture, in order to understand how the measurements, say in a gamma ray thought experiment of one property, even if we're treating both the electron and the photon as corpuscular, how nevertheless the measurement that we take in the image plane will be different than will disallow us to make further predictions about the properties we could learn from a measurement in the focal plane and vice versa. So that's, I think, the usual sense in which most people understand complementarity as playing a role in understanding Heisenberg's uncertainty. And then the third way is where Kant comes in a bit more. It has to do with complementarity between the classical and the quantum modes of description. So this is where you should take a big drink of coffee and prepare for some Kant. You know what? I missed something earlier on, which is rather important before the Kantian analysis. So when the second point here, that even though quantum mechanics presents insurmountable limits on predictability and still involves causal chains, she was pressed on this point, this retrodictive causality point, quite a lot by Paul Bernays in particular, who was a fellow Nelsonian and also, a mathematician. And in a sense, Bernays' critique, which is that retrodictive causality is not an adequate, is not a robust enough sense of causality. In fact, because it doesn't, Bernays, so he says that such a process, i.e. retrodictive causality, does not in general allow us to specify a unique causal chain, and this due to the failure of one-to-one mapping between the states of the system and the apparatus. And yeah, this is correct. And it seems from Hermann's response to Bernays that she understands that, if you want to put it in modern parlance, her retrodictive causality thesis is not going to answer the question of specific outcomes, because you cannot recover this you cannot point to a unique causal chain retrodictively and say this is the one that caused the outcome on the screen or whatever, but nevertheless that it was in the context of a particular experimental setup. But she does maintain that retrodictive causality is a satisfactory answer to the puzzle of how some definite outcome is in fact measured. And she thinks that that latter solution is enough to demonstrate that causal continuity of some sort exists. So even our failure to pick out a unique causal chain is not enough to kill off a Kantian causal conception. Okay, so sorry. Now back to the Kant bit, and I will be a little bit quicker on this point. So again, complementarity allows us to understand, I mean, we know why we need to bring mutually contradictory aspects of the theory together. It's because we observe contradictory aspects, wave and particle duality for both light and matter. But how do we do that? How we do it is by this application of the threefold complementarity, right? So the Heisenberg uncertainty relations in particular allow us to bring together in one form, one equation or other, side by side, mutually contradictory measurement possibilities. But this other aspect, the complementary modes of description, this is what allows us to use the unintuitive symbols in quantum mechanics. I mean, what on earth is a wave function? What on earth does it correspond to in reality? It's not an intuitive symbol, but nevertheless, it is what allows us to retain a sense of causal completeness because, of course, Schrodinger's equation and the wave functions that solve it are within the context of a single experiment and between the interaction between the collision between a photon and an electron and the measurement of the photon that has refracted up into the microscope. In between those two measurements, of course, the Schrodinger equation has evolved deterministically. So that is a deterministic, it is a causally complete description, but we must bring it alongside other aspects of the description that are, where we must loosen our grip on sort of intuition, right? So the benefit of the symbols, like wave functions, operators, eigenvalues, eigenstates, and so on, is that they allow us to recover a logically and causally complete and coherent formalism. And again, she's going to argue we rely on these symbols to bridge the gap in quantum mechanics between the data of our observation and the formalism, because the data of observation present complementary descriptions of the world. They cannot be reconciled except through this formalism. This formalism is unanschaulich, it's not intuitive, it's not understandable in a direct immediate way like classical concepts were. But nevertheless, it is what we need to perform this theory observation connection, which is important for scientific understanding of any sort. It is this sense that the third complement, the classical mode of description, allows us to use unintuitive concepts in an analogous way. So we can use not just these new symbols like the wave function, which really doesn't have a strict classical corollary, but words like position and momentum, and here you hear echoes of Heisenberg. But when we apply them to the quantum description, because the formalism only relates in this analogous way and in this complementary way, relies on the classical mode of description, we can never say that those terms are being used in the traditional sense, but instead they must be being used in a deeply qualified sense. Okay. So the bridging the links, doing so with bridging the link between data and theory is still only letting the use of analogy play the usual role that it plays in Friesian interpretations of Kant. But what what Hermann brings further is this claim that due to the relative observation the relative context of observation, namely that we can only maintain a causally complete description of quantum mechanical phenomena of events within one particular setup, right? And understanding holistically not only the collision, say, between the photon and the electron and its passage through the microscope, but then the physicist's choice of at what level of inside the microscope to place the photographic plate. And so from this holistic perspective, once I've set up the apparatus, I've made the context of the measurement well defined, then I can tell my retrodictive causally complete story. But there is no sense in which I can recover a causally complete story independent of this description of the context. So I cannot tell you that no matter where I measure or how I set up my measurement, these are the properties we will measure for the collision between the photon and the electron. Instead, it will be restricted to this particular experimental arrangement. So again, this claim that due to the relative context of observation, no connection between the data of experiments and the formalism, even in classical mechanics, can be simply interpreted, can any longer be interpreted as absolute or objective. She's going to say that because at the quantum level, the context of observation matters. That means that at all levels of investigation, the context of observation is going to importantly qualify the results of our, or the conclusions we can draw. So all such connections between data and theory, in a way, must be interpreted using analogous analogy-based concepts. So this is the Friesian view. So the constraints of the uncertainty relations bridge can only exist and can only meaningly refer to its relata when the whole contraption, the bridge plus the relata, are applied within a single observational context. So this is going to motivate how she interprets the wave function too. Bernays is going to push her to say, look, the wave function should be interpreted purely in this, I can't find this, as only being this probabilistic interpretation. Bernays wants to push the probabilistic interpretation or the ensemble interpretation of the wave function. And Hermann reminds him that only a complete description of the wave function is one that includes the, quote, complementary double character. That is, that within a single observational context, the equation, the wave function can be understood as fully deterministic, but nevertheless, when we attempt to apply it or understand the wave function or interpret it across observational contexts, it loses that deterministic characteristic and can only be described as representing probabilistic outcomes. So there are revisions, upshot, and I'm closing now. I know there's a lot I've gone over. There are revisions forced on the philosophical viewpoint, in fact, the neo-Kantian viewpoint by quantum mechanics, but it doesn't have to do with causality, because she thinks she's demonstrated that quantum mechanics is causally complete retrodictively. But rather, she says that a Friesian interpretation of the categories of understanding, i.e., in particular causality, coupled with the necessity of describing natural processes only ever with respect to a specific context of observation, compels us to abandon hope of ever developing a unified or absolute scientific framework, which is objective and which can help Nelson accomplish his Hilbertian task of axiomatizing all knowledge. Right. So she says, again, and this will be what I end on, if the physicist wants to understand Kant's principle of causality as just the strict, that each effect has a necessary cause, she says, then the physicist is left with a strangely empty formal schema in his hands, whereby one would need to locate precisely the defined causes for every event in increasingly infinitesimal time periods. And that's clearly impossible, and also not what we're doing when we do science. Because what we really do in the pursuit of scientific understanding is couple causal relationships with various other spatial and temporal observations, namely through the application of differential equations, right? And when we do this, we lose our ability, even in non-quantum mechanical arenas of physics, we lose our ability to describe or to trace specific cause-effect chains. But instead, we are doing a more capturing only a more coarse-grained suite or network of relationships. And she says what we do when we use differential equations goes beyond any pure application of the cause-effect relationship in Kant. And then Fries allows us to do better, because when we can apply causality in this analogous way, it allows us to say, okay, let's reinterpret causality as merely like what we do in practice in science, using differential equations to capture a network of causal relationships via differential equations is sufficient for us to do our physics and to adequately explain and derive understanding from the data of experience. Okay. So I think I had a bunch of other quotes, and I will post these slides so that you may read them later if you like, because I feel maybe that was not super coherent. But again, I don't want to say much more other than that. And this this deeply neo-Kantian approach to sort of a Bohrian interpretation of quantum mechanics is a very novel interpretation, not only historically, like in the 1930s. And remember that this Locus Classicus, her 1935 essay, was written before EPR, and in fact published several months before EPR. So she's just putting her pen right on the spot very clearly in many of these arenas of debate, and doing so in a way that, is novel and very clear, but also it's a very new way, compared to contemporary interpretations of quantum mechanics. And neo-Kantian interpretation of quantum mechanics brings a sort of nuance that we've, I think, maybe lost when we talk about just whether we're doing primitive ontologies or understanding the wave function as epistemic or ontic. Those are fascinating views, and I like some of them. But this perspective is another way of, it doesn't just sit between epistemic and ontic, and it doesn't just sit between realism and instrumentalism. It's something quite a bit more nuanced. So those were my concluding remarks, and I'd be happy to answer a few questions in the 3 minutes we have left, but also in the hour we have later on. So thank you.
Thanks so much, Elise. That was wonderful. So we are a little bit short on time, and I want to make sure that we have a time for people to take a break, and we will be able to come back to this discussion in the final hour. I saw that Carl has his hand raised. I think we may only have time right now for Carl's question, and we'll have to save the other questions for the end. So Carl?
Thanks, Elise. It was really fascinating, and it makes me want to go out and read these essays by Grete. I don't understand this retrospective kind of causality very clearly at all, and so I need to work on that. But insofar as I was grasping at the idea, it did strike me as very reminiscent of a pilot wave type picture. If you've got a wave function, and you think of the differential equations as giving you the causal story you need, you've got the Schrodinger equation, and you've got that giving you the causal story, and you don't believe in collapse. Well, it sounds like you're very close to a pilot wave picture. Did she connect at all with de Broglie?
Guido, I defer to you. I don't think she doesn't cite de Broglie in her 1935 publications, and in her correspondence she doesn't talk about de Broglie, but that's something you notice too. And then it's very tempting to say, well, since she kind of understood that there are different types of hidden variables one might supply, and yet she's giving something that looks like a de Broglie-Bohm theory, one can speculate. But yeah, Guido, does she ever talk about de Broglie?
No, she does not. Nor does she ever comment on Bohm later on,
Right.
although she may have encountered Bohm's work in the 1950s when she visited Weizsäcker again, because the semester when she went to visit Weizsäcker, they were going to discuss recent hidden variable proposals in Weizsäcker's seminar.
That's right. Yeah, so it's unclear whether she, and in her correspondence, she never mentions reading either of those guys.
Nope.
But yeah, there's definitely more investigation to be done. Yeah.